Physics promises to deliver for us leaps forward in our technological capabilities. But his time in the field has shown Dr. Noah Charles that physics shares unexpected connections with many other areas of thought, from philosophy to social science. And that is what we'll work to unpack in this conversation here. Hello and welcome to the Jefferson Educational Society's digital programming. I'm Ben Speggen. I'm the vice president at the Jefferson and am a contributing editor at the Erie Reader. Now, my guest for this conversation is physicist Dr. Noah Charles. In this conversation, Dr. Charles will explain how his interests in statistics led him down the rabbit hole to questions of the evolution of the universe and our expectations about its future, and simultaneously to work he's doing to understand why people of non-traditional backgrounds sometimes choose to leave the STEM field. His experience demonstrates the fascinating interplay between hard science and many other disciplines, and we'll cover that here in this conversation. Now, Dr. Charles is a recent doctoral graduate in physics from the Ohio State University, where his research focused on localization transitions, the change in the behavior of free electrons in a material from being localized to a particular region to moving across the entire material sample. Now, I promise we're going to see some great images to understand all of that. And his work in this area has focused on the phenomenon of universality, the tendency of seemingly unrelated systems undergoing certain phase transitions to behave similarly to each other. Dr. Charles's interest in statistical physics led him to the intersections of physics, math, and philosophy, where one may ask questions about the models abstracted from their physical details and where the modern research is ongoing into basic questions. Now, since this program is first airing live on the JES Facebook page, we'll work our way through as many questions from you, the viewers, as we can as we host this event. If you have a question, just leave it in the comments section below. If you're watching or listening to a later broadcast of this event, please still feel free to send us your questions and comments and keep the conversation going. We'll do our best to get them along to Dr. Charles. And for more information about upcoming Jefferson Educational Society programs and publications, please visit jeserie.org. Be sure to like us on Facebook, follow us on Twitter and Instagram, and subscribe to our YouTube channel. Dr. Noah Charles, thank you for joining me for this conversation.
Thank you for having me, Ben.
So, Dr. Charles, for those needing a refresher or perhaps an introduction, what is, simply put, statistical physics?
That's a great question, Ben. So if anyone's had a physics class before, you may have seen something like a ball being thrown in the air where we trace out its path over time. Now there you can describe the ball's position at each time. You can describe its velocity at each time. In some sense, you know everything that you need to know about the ball. But that's not really how things work in the real world most of the time. For most materials, you might know some information, but not very much. So for instance, if you have a bunch of particles in a box, maybe it's a gas, then you might know the pressure and maybe the volume, you might know the temperature, but you certainly don't know the complete description of every particle's position and velocity. And so that's what we mean by statistical physics. How do we come up with sort of statistical averages of properties when we don't know what are called microstates, the complete descriptions?
So, Dr. Charles, it's a fascinating area of study. What drew you to this? Why were you interested? What was this a path that you always saw yourself heading down, or was this something that you came to later in life? How did you get your start with statistical physics, something you're clearly passionate about?
Oh yeah, so I would say that, like most people who go through undergrad, I didn't know exactly what I wanted to do at all. I actually had two majors and a minor. I was a little bit undecided about what my path would be. But after I worked in a lab in undergrad, so doing experimental physics, I realized that I was really more drawn to the sort of mathematical side of things. And so my first week in graduate school, I was walking down the hall trying to talk to people, and I bumped into my advisor, or the guy who became my advisor. We chatted about statistical physics, and I sort of realized that I'd found a home. I think that's probably the best way to put it.
So, and you found a home there, and you continued on. You just finished your doctoral work. Let's talk about your dissertation.
Sure.
What does it cover? What new ground are you breaking? What connections are you making here as we're discussing the unexpected connections? So what did you work on for your dissertation?
Sure. So my dissertation was called Multifractal Methods for Anderson Transitions. So I want to leave aside the multifractal part of that for a second and just talk about what an Anderson transition is. That's probably a good place to start. So an Anderson transition is a type of phase transition. You might be familiar with these, right? An ice cube melting in your water glass, that's a type of phase transition. Really just materials changing from one sort of generalized kind of phase to another. In Anderson transitions, what you're going from is localized phases to delocalized phases. And a localized phase is you seem to know a lot about this, Ben. As you described at the beginning, is where an electron might be in one part of the material for very, very long periods of time, whereas an extended phase is where an electron will travel all over the material. So the most common type of this is just metal to insulator transition. You'll notice that many metals, if you, or I should say many materials, have a one metallic phase and one insulating phase. And the transition between that with temperature is an example of an Anderson transition, if we sort of ignore the fact that electrons interact with each other, which is a pretty common technique in this part of the field.
So I appreciate the ice cube as the example there, because that helps make sense to me. And in my introduction, I've got to say, Dr. Charles, I took a lot from what you wrote about your description for this. So I am an eager learner. My curiosity is piqued here, but in no ways, in undergrad for me, I was bumbling my way through figuring out what I wanted to do. I was doing that as an English major. So there's a reason words are more, more of my wheelhouse and not what we're looking at here, but I'm really curious about it. So you unpacked Anderson transitions for us. So tell us about the rest of your doctoral work and then how that makes sense. And perhaps there are some other slides you can show us so we can get a better understanding of what it is that you're focused on.
Yeah, certainly I have a few. So I'm focused on one particular type of Anderson transition, the one that happens in the integer quantum Hall system. So let me talk about what that is. Suppose we take a so-called 2D electron gas. Now all that means is that we've confined the electrons in a material to move only in one 2D layer, which is sort of challenging, but was possible by the 1980s. Now we lower the temperature. In fact, for the models that I deal with, we work at 0 temperature. And then we put a strong magnetic field through the sample. So if this is our sample right here, then the magnetic field will go in the direction that's up, and we'll run a current in this direction and measure the voltage in this direction. The resistance that we get from that, just V over I, is called the Hall resistance. And what was found in 1981, actually somewhat surprisingly, is that this resistance is quantized. It has these sorts of flat parts, and then it jumps between the flat parts. And these jumps are this integer quantum Hall transition, this phase transition that I'm interested in. So basically, we can describe in a pretty simple way what's going on here in terms of a tuning parameter. So that's usually the case with a phase transition. If you have an ice cube melting, then the tuning parameter is the temperature. As the temperature rises, the ice cube melts. So here, what we're usually tuning is either the energy or the magnetic field. I'll talk about the energy because it's a little bit simpler. What happens is that as we drag the energy up, what you're looking at is how many states are located at that energy. What do I mean by states? Well, electrons can be in a certain collection of states, but not anything. There are only certain states that are allowed in the system. This is one of the fundamental principles of quantum mechanics. And so there are some states here, there are some states here, and there are some states here. In the middle, what we get is this these states that do exist, but are localized, whereas these states near these transitions will be extended. And so that's what you get in this green region. So we get many delocalized states, and that leads the material to sort of act metallic for a brief period. So I want to talk, actually, let me go back for a second here and just talk about this localization length that I'm talking about here. The localization length, remember that our electrons in the localized phase can't go very far. What's going on is that as we get into the extended phase, the electrons are able to go all over the sample. And the distance that they can go is this E minus E critical, which is this central energy, to some power. This kind of power law behavior is completely typical of this kind of phase transition. And we'll talk about that a little bit more in a second. Now, this slide is probably a little bit confusing if you aren't a professional physicist who studies the integer quantum Hall transition, and I don't really want to talk too much about what's going on, but all I'm getting at is that very, very precise experiments are able to measure this exponent extremely accurately to at least the 100th place. And what we find is that nu equals 2.38. Remember this new exponent, this localization length exponent, because it's going to come back. One other thing that's very interesting and where this multifractal business comes into things is that at the transition, we don't exactly get local or extended wave functions. We get these strange multifractal wave functions, which basically form some kind of a fractal pattern. That's actually the direction that my research went in, but isn't critical for the rest of the talk. I just love this image. It's so cool. So let me again talk about this exponent. The reason we care about this is because of the theory of universality, which basically is this completely general theory that applies to all so-called continuous phase transitions. And we won't worry too much about what that is, but I will mention that this ice into water is not an example of one. But that water into water vapor can be an example of one. All right, so the transition is again driven by some parameter. In this case, it's the energy of the highest energy electron in the system. And it occurs when the parameter reaches some value. Then we find that some observable will diverge. In other words, because this exponent is negative, psi, this Greek letter, is going to infinity. And so as we get close to the critical energy, this diverges. And this power law of behavior characterizes not just one system, but many systems, which we say are in the same universality class. So we can learn a lot about systems that we haven't even really studied yet just by looking at these exponents. The reason we can learn a lot is that actually these exponents don't depend on anything microscopic about the system. Again, they don't depend on all of these possible degrees of freedom. They only depend on a few things, these kinds of symmetries, what dimension are we in, maybe some global features, and I can answer questions about that, but I don't want to get too far into it. What I do want to say is just that maybe I've never studied system X before, but I know that it's in the same universality class as system Y, and I do know things about system Y, then I could tell you things about system X. So it's a sort of cheap way of getting much more information about a system than you might think that you could get.
And so I love this image that you just brought up. And so if we could go to that to see how that is now playing, and we can see it visually, what you're looking at.
Yeah, sure. So before we get sort of too in the weeds with this universality stuff, let's just look at what happens when you put electrons in a magnetic field. And for the time being, actually, let's make them not quantum electrons, but sort of just classical charged particles. Now, what are we looking at here? We're looking at electrons confined to a 2D sample, but we're allowing that there are some impurities in that sample. Those impurities cause positive and negative charge to accumulate in certain places. The model that you should have in your head is that places where negative charge is accumulated are like hills, and places where positive charge is accumulated are like valleys. And the reason that we have this hill-valley analogy is because charge opposes like charge and attracts opposite charge. Okay, so if there were no magnetic field, you would get sort of the normal behavior of a ball in a hilly landscape. It rolls down the hills, and you might see it going back and forth or something like that. But the presence of the strong magnetic field means that instead we move along the hills, which is sort of strange behavior. But you'll see it happening here. This is a real simulation of these electrons moving in this magnetic field.
So that's our classical electrons. So again, just differentiate the difference that we're seeing when we're looking at it in what you're talking about in a non-classical sense.
Absolutely. I'll get there in just a couple of slides. So let me talk first about these edge currents that we do see even when we're in a localized phase. So that's one sort of strange bit of this, but that we do get some current that can move through the system. The reason for that is that at the edge of the sample, there must be some hill. That's why the electrons don't escape. And so because we're moving along the hill, we get these edge currents along the sides. But electrons here in the middle will actually be trapped on individual hills or individual valleys, depending on exactly the energy. Now let's move into this quantum case that you were talking about. What's going on here is that in quantum mechanics, we can't say exactly where an electron is, even if it's localized at some point, as in we know kind of where it is at some initial point. It may spread out all over the sample as time goes on. And that's what you're seeing here. As the electron moves along this hill, it's able to so-called tunnel to a nearby hill. That wouldn't be allowed for a classical electron. And so you get the electron's probability of being in one place splitting in two. So there's about a 50% probability that it's on this side and a 50% probability that it's on this side. All right, so now if it's able to do this very often, that is to say there are many hills that are nearby to each other or many valleys that are nearby to each other at the energy level where the electron is sitting, then our assumption that the two sides in this last slide don't talk to each other and we get these stable currents breaks down. Instead, the electron is able to move all over the place as it jumps from hill to hill to hill. Let's kind of look at what that would look like. So at a low energy, we would get the electrons moving around these blue regions, and they would move either clockwise or counterclockwise depending on the direction of the magnetic field. Now maybe these are valleys. These valleys aren't anywhere near each other, so the electrons don't really tunnel between the hills, or I should say valleys, sorry. As we increase, however, the valleys get nearer and nearer each other. And at some point, we get to a sort of critical point, and again, this is the phase transition that we're talking about, where many valleys are near each other, and the electron has a significant probability of tunneling one place to another. And that's how we get our extended behavior. Instead of just being stuck on a single valley, the electron's able to hop all over the place. But then as we keep increasing, now the electrons are instead localized to these hills or to the edges. And so we just very briefly pass through this period when the electrons are able to go wherever they want.
So, Dr. Charles, one of the unexpected connections that you find in this, because I want to wrap up this portion of the conversation soon and move on and talk about the connections to philosophy, because I find that fascinating as well as the look at diversity and equity in STEM education and the work you're doing there. But I can't help but in an earlier conversation, you and I were talking about this. One of the unexpected connections that you had mentioned to me was gravity.
Absolutely.
And that begins with quantum gravity. And you have me, but I need an explanation on that. So what is quantum gravity? How does it fit into what you're focused on here today?
Sure. So let me maybe jump ahead to a later slide, and then we can kind of come back. So what happens in Einsteinian gravity, the theory of general relativity that maybe you're familiar with, is that matter causes space-time itself to bend and curve. That kind of curved surface affecting things is exactly the same thing as what we see in this system. Now that seems bizarre. What happens is that as we have these hills that are near each other, and the place where they're nearest to each other is called a saddle point. The way that the saddle points are actually laid out is random, effectively. It's so-called disordered. And this is actually the direction that my dissertation work went in. Now, if we take sort of this lattice of saddle points connected by these abstracted links that represent the electron moving along the hillside, we can imagine putting a dot in the middle of every one of these. Notice that everyone has two coming in and two going out. That's just from this hill-valley structure that we had. So we get something like this. Now, if you sort of squint at this and imagine it popping out of or into the page, we do get a sort of curved surface. In other words, if we force each one of these to be a square, we don't get something that sits flat in a plane anymore. We instead get something that's bumpy. And if we take that to a large sample, we get something like this so-called quantum sphere here. And that's exactly what we're doing. Now, because we don't exactly know where these saddle points are, again, we're doing statistical physics here, we never quite know where everything is, we have to average over things. And that's the sense in which this is like quantum gravity, where you have to take these curvatures and average over different possible curvatures. That's a huge task that hasn't been really accomplished yet, but in some sort of regulated settings, you can do it in a quantum gravity setting. We are actually helped by the fact that we have these real saddle points. So we don't get the same sorts of errors that quantum gravity theorists get. But we are able to borrow from what they're doing, which is really cool. And they're just, these unexpected connections between fields that you wouldn't think of being close to each other can be really, really beneficial as you try to proceed along some new direction.
And so not being able to pinpoint exactly down, but working with what you have to figure this out, do you find that frustrating or invigorating in terms of trying to move toward finding better answers as you're conducting this new research?
Of course, like any work, it really depends, right? I mean, I think everyone in their career, right, will have periods of time when things are moving really quickly, where things are really exciting, and periods where it's frustrating. And I think, you sort of know that you're in the right place if the frustrating periods pay off at the end. They feel good when you finally get the answer.
All right, so Dr. Charles, one of the things we talked about as well is your unexpected connections into other areas of study, and one of those happened to be philosophy. So how did your interest in what we've just been talking about and your work in statistical physics, how did that bump over to a very different discipline in philosophy? What drew you there?
Sure. So, I mean, at some level, this is always partly interest and then just partly social. So I actually happen to know a couple of philosophy PhD students at Ohio State. And so, we got together, we started talking and realized that a lot of our interests were aligned. There's actually a huge community, or I shouldn't say huge, huge maybe in the sense of philosophy, that does philosophy of science and specifically philosophy of physics. And one place that my background came in was this localization stuff. So let me actually go really quickly to just a really broad categorization of how dynamical systems can evolve. So very quickly, let me say a dynamical system is a system that has a state at some point. There are rules for how that state evolves into later states. And that's really it. All of, that really encompasses things. So basically, in dynamical systems, you get kind of two types of behavior, or maybe two ends of a spectrum. On the one hand, you get systems that are localized. And what I mean by that is just that states usually, or almost always, come back to themselves after some period of time. On the other hand, on the other sort of end of the continuum, we get ergodic states, or I should say systems, where the states never come back to themselves and sort of just meander all over the possible configurations of the system. In the middle, we get more exotic things like our multifractal states that I was talking about before. So this actually gets into maybe an interesting area of philosophy that, I know we've talked about a little bit, and it's just so cool. But the second law of thermodynamics, which I think many people have heard about in a sort of layman sense. And I think you should start with this intuition and see sort of where it leads. So, right, if you had to explain the second law of thermodynamics to a 5-year-old, you would probably say something like, well, there are some systems that are sort of more simple, and there are systems that are sort of more complex. And so if you go from simple to complex, you can't go back. So you can crack an egg, but you can't uncrack an egg. Once you've beaten it or made a sunny side up, egg or something like that, it's impossible to go back. And just to make that a little bit more formal, what we would say in a sort of Physics 101 class is that we want to take the natural log, it's not particularly important what that means, of the number of microstates in one macrostate. Now remember, we talked about microstates and macrostates before. Macrostates are the ones that, and that's a typo, sorry about that. The microstates describe all possible degrees of freedom in the system, whereas the macrostates describe just what we can observe. The idea would be that in an uncracked egg, there are sort of a lot fewer ways that you could configure all the atoms to be uncracked than there are in a sunny side up egg. That's sort of way, way more ways of arranging that. And so that's the reason you can't go back, as we would say, or as we would think. The problem is that this is not true, and this ended up being the source of a major controversy in the 1890s, which I'll talk about in a second. So let me first say what the problem is. And when I heard about this the first time, I think my mind was just completely blown. So I hope I can impart how sort of stunning this is. But there's a theorem due to Poincaré, who's a French mathematician that people may have heard of. But in any case, if a dynamical system is finite, that is to say, it can't, it doesn't go on forever, and it's isolated from other systems, then necessarily localized, ergodic, anywhere in between, it will eventually return to a microstate arbitrarily close to the microstate in which it started. So here's the example that I've given. If a box of gas has all molecules on the left side, of course, what you would expect is those molecules will expand and fill the whole box. But what this tells us is that if we wait long enough, we will come back to a configuration where all the molecules are on the left side again. And that goes against all of our intuition about how the universe works. And that's sort of the problem. So prior to this controversy, a guy named Boltzmann, German physicist, had sort of worked to make thermodynamics, which people sort of understood, second law, of course, is of thermodynamics, and make it about statistics. It's really just about the fact that these configurations where the molecules are all over the box are much more numerous, and so you're much more likely to end up in one. And he came up with ways of deriving the second law. Then a mathematician named Zumelo, who was a postdoc at the time in 1895, wrote a paper and was like, no, this is impossible, of course, because if this system is periodic, it can't also have entropy that always increases. That's just impossible. And so the second law must be wrong, or some other part of this framing is wrong. And this is the sort of philosophical landscape at present. And I should say no one has ever answered this question. We're still completely confused, and you'll see talks by extremely notable physicists Nobel Prize winners and things like this about how this affects maybe the arrow of time and things like that.
So how intently are we working on this to figure this out? Because like you said, your mind was blown earlier. Mine is as well. Where are we getting? What's the progress being made from physicists and philosophers looking at all of this right now?
Well, there's actually, I would say, not too much interest in terms of the whole scope. If you just look at where all of the money goes, right? Almost all the money goes to things that will come to some sort of more to a quicker fruition, maybe, or something like that. And these are sort of smaller, but I wouldn't say none. I mean, there are people, and as I said, eminent people who work on this kind of thing. And in fact, Boltzmann himself already had answered this question. He gave some possible solutions, which I have basically just stolen from him. And we could come up with a couple of these sort of easily. One is that, what if the system is infinite? What if our system that we are thinking about is infinite? Then there's no problem. Maybe the system is not isolated. Maybe it's coupled to other systems, then we're okay. Or maybe, and this is maybe the strangest thing, we just happen to look at the system at a time when its entropy was really low to begin with. And so it will eventually, the second law will reverse. But that won't happen for a long time, and actually won't happen very often. It will mostly be on this other side.
So an audience question coming in, I think, is asking about like what, defining the word here, system. So what do we mean by system in terms of ours could be infinite? It could be coupled to another system. What are we looking at here, Doctor?
That is a fantastic question, and of course one that I'm glad someone asked. A system is just any collection of degrees of freedom that we have decided that we are interested in. So one system that I could come up with is my whole body. Another system that I could come up with is the left half of my body. Now, these might be not that useful in terms of an analysis of statistical physics. The reason being that I'm so strongly coupled to the environment around me, right? I am suspended in the air, and in fact, if all the air vanished, then I would just immediately die. I would not function the way that we expect that I should function. And so it might make more sense to look at a bigger system, maybe the system of the whole Earth or something like that. But in any case, any collection of a number of degrees of freedom is a system. So usually that will mean a collection of atoms, their positions, and their momenta at some point.
So another audience question, looking at laws and how they go from being true at a particular time to then untrue. How often or how common do we see that as discoveries are continually made? Because you say one of the options here is the recurrence time could be longer than we're willing to wait. And your sub-bullet point there, the second law isn't true in general, but is true right now and for a long time. How common is something like this in your field?
I would say that in these sorts of fundamental questions, this is exceedingly common. Because usually the question is so fundamental that we don't have a direct way of accessing the solution. So for instance, the electron charge is something we know very, very well, and we've measured it to maybe 11 decimal places or something like that. And so basically, the only thing that happens on something like that is we refine and refine and refine. We get better knowledge, but we don't sort of fundamentally change our knowledge. But on the fundamental question like this, where it's not even clear what an answer, what would constitute an answer, we often end up with wildly competing theories and big holes in some of the main theories that eventually get pointed out.
So I'll bring it back to another question I asked earlier. Is this fun or frustrating for you when we're looking at unpacking this?
Oh, this is super fun. And I actually have my own little way of thinking about this, this particular problem, which is that if a system is ergodic, and again, this brings in my background and is one of the reasons that it's so fun to play with these unexpected connections. If the system is ergodic, then two points that are initially very near each other, that is to say two configurations, these aren't specific points in the system, but two configurations the system could have, will evolve very differently as we wait. And so even though each one will recur, they'll recur at very, very different times. And so if entropy represents not the number of microstates in the macrostate, but our certainty about how the system will be at a particular time, even though we know that recurrences will happen, we really don't know when they'll happen. And so we can say something like, look, I'm just completely uncertain about the future. So entropy increases in the sense that my certainty about what the system will look like in the future decreases. The problem with my solution, and something that people have brought up about this method, is that it also means that entropy increases as we move into the past. So the second law is true in both directions. Maybe not the best solution, but one that I came up with as I was playing with this. And the kind of fun you can have if you're willing to sort of explore the boundaries.
So, Dr. Charles, that seems like a big takeaway here, that, we're continuing this conversation and we're finding out we don't know all that we think we know about entropy, and we're looking at your contributions before we move into the next section to talk about diversity and equity in STEM education and your work and experience there. What else should the audience take away from the connection between statistical physics, or just physics in general, and philosophy, and how you were able to look at those two fields of studies and marry them in a way that perhaps they were not married before?
I'm so glad you asked, Ben, and certainly I am not unique in this regard. There are, maybe on the order of hundreds of people in the country who do this. I think that physicists have ignored philosophy in the 20th century in a way that's sort of should make your mind a little bit confused or something like that, because it seems so essential to physics. But sort of fundamental questions, like questions about what does quantum mechanics really mean, haven't answered that. How is quantum field theory true when there are certain problems with it at the limits? Haven't answered that either. I mean, there are many places where there are questions that we can ask, and that, it's not clear without some philosophical knowledge what would constitute an answer. There was a philosopher, Thomas Kuhn, who worked on philosophy of science in, I believe, the 60s. And his whole idea was that as society changes, we sort of change what would even, mean for us, or what would serve for us as a compelling answer to particular questions. So if you're Aristotle working in ancient Greece, you don't need differential equations that tell you about the future of the universe to feel like you have a compelling answer to a question, but we do need that. And so I think that these kinds of questions of philosophy are so important as we grapple with the fundamental aspects of physics.
So for quantum mechanics, audience question here as well.
Sure.
For quantum mechanics and the types of things that you're studying, does it help or hurt when pop culture ventures into your realm? And this example is taking a look at the time travel that we've recently seen in the Marvel Cinematic Universe. So
Yes.
does it help people understand this? Does it complicate the issue for you as an expert, as a scholar, as a physicist? Is it helpful, or do you think this is hurting when we look at this in pop culture?
Oh, I mean, I think it's fun, I guess. Ant-Man had which is the movie that started the time travel thing, had a physics consultant, I happen to know. And so it's so kind of funny. There are really specific, correct parts of it, and then parts of it are just completely fanciful. It's okay to have fun with it as long as you sort of know that you're having fun. And I actually do think there's a sort of knock-on benefit in that if people maybe get interested in these questions, they might go look up the real solutions. So I would say as long as you take it with a grain of salt, it's all to the good.
So it is fictional. We need to keep that in mind, but at least it's a pathway, a conduit to get us there to maybe studying it in a non-fictional sense and actually taking a serious look at the science. Well, let's take a serious look at diversity and equity in STEM education. So aside from all that we've covered here that you've studied, from your doctoral work to your interplay between physics and philosophy, you explored challenges of diversity and equity in STEM education and are involved in some initiatives. Tell us what you found and tell us what work you've been doing.
Sure thing. And so let's move on a little bit. Well, what I kind of noticed as I was talking with people through my second and third years of graduate school is that we saw a big gap in how undergraduate education is handled, in that there's just this crisis of retention, and it's true at Ohio State as it is at other large public research universities. It's even true in general. And it's not easy to explain when you start looking at the data, which we spent a while doing. So, just looking at the numbers here, of course, they're kind of galling. Physics lags far behind other STEM fields itself. And so that kind of suggests to you maybe there's something unexpected going on here. And then the data that I think started to really convince me that this was something that we needed to, or we could address ourselves, was the data that indicate that even when we control for academic achievement, students from minority groups, and by minority here, I mean minority in STEM, so would include women, for instance, drop out at higher rates than those from majority groups. They just don't stay in the field. And that means two things. First of all, of course, it's fun to do physics. I really like doing it. And it's sad for me that, people who might be interested don't get the chance to do it. And the second is that it's a loss for science, because of course, there are many competent people who, again, we control for academic achievement would have succeeded if not for these maybe extra academic factors that end up dropping out. And that's really a loss. We would see a lot better, I think, scientists if we took time addressing this kind of thing.
Right, and Dr. Charles, just on your previous slide, I wanted to point out, as we see the increase of women obtaining bachelor's degrees, going to college, and we see that market uptick, it's still not there in physics, and it's still not there in STEM education, even though, women are now earning, more than 60% of degrees. We don't see it in STEM. So what were some of the, you said you controlled for academic achievement. What were some of the factors? Walk us through that you're seeing, and then some of the steps that you're taking to offer some solutions to, correct that retention rate, and to see more people, more minority candidates in the field of STEM, stay in the field of STEM and be successful, so that it's not a loss for them and it's not a loss for science.
Sure. So one thing that we notice very heavily is that persistence varies a lot by institution type. So as I mentioned at the beginning, large public research universities, you can do a control for this with there's the so-called Carnegie classification. That's the R1, R2, et cetera. So R1s have the biggest problem with this. And that's sort of strange because R1s don't necessarily attract the best students across the board when you look at that data. What seems to be happening is that there's something about this sort of large impersonal culture that's harder. And this is actually where I wanted to go, that these cultural factors seem to really be the determinant. And that's true when you just ask people. I mean, of course, anecdotes are not necessarily data, and of course you need to sort of be careful about who you're asking and things like that. But I do think it's compelling to just listen to what students from many minority groups, and I should say we should include things like first-generation students, transfer students in there as well, what they say. And what they say is always that, it's very challenging often to be in a culture that doesn't really want you there in the first place, and that doesn't see you as a valuable member. And actually, as this comes to another unexpected connection, which is, as I, sort of branched out myself and allowed myself to explore my other interests, I realized how much of a culture sort of difference there was between me and some of my more sort of hard-nosed peers who wanted to sort of keep physics the way that it always has been, or something like that. And that, I think, we have to resist that kind of tendency, right? There's this sensibility that when you're teaching a physics class, you should target the nerds, right? You should target the guys on the Big Bang Theory. And I think that does a disservice to a lot of students who don't see themselves as the guys from the Big Bang Theory. Maybe they like to play basketball or lift, or maybe they like to, I don't know, go watch terrible movies. Maybe they like to examine the time travel from Ant-Man. Who knows? But that kind of breadth is something I think we should really be pushing for, and something that we sort of tried to address with some interventions. So before I move on, I just want to point out that we do have these factors that are studied in the literature at length, and that maybe the keywords, if you want to sort of look into this kind of thing yourself: science identity, self-efficacy in the context of science, and sense of belonging. Those are the three that we looked at the most. So what would an intervention be like that we could do ourselves? That was really the question we started asking ourselves. And of course, we want it to be evidence-based, right? We don't want to just do whatever we want. So we did spend a long time looking just at what it looks like, what the sort of landscape looks like in STEM education. We wanted to be cost-effective because it was just a bunch of grad students doing this. We didn't have infinite resources, and the resources that we got, we had to sort of spend a lot of time fundraising, and that's a trade-off when you could be doing other things. We want to be able to respond to fluctuations in student population. And that's actually a big deal when you might have at Ohio State only a few Black students a year, maybe only a few Hispanic students a year, a few women students a year, and that could change a lot year to year. So you need something that's sort of modular in a sense, that can sort of adjust for those sorts of big years or small years. And we did want to see retention over change over just a few years. That was another thing. So what I ended up doing with some friends and colleagues is establish a mentorship program that paired freshmen and sophomores with graduate and upper level undergrad mentors. So we started this out, just with a pilot, and then we turned it into a class for which I was the instructor. And we did all kinds of fun stuff, but a major part of this was just getting the students to know each other, since we were targeting students from these underrepresented groups. And that kind of cohort building was really important, we found. it was so important that we decided to branch out into a summer program where we brought freshmen before the school year started to Ohio State to sort of meet each other and work on some science projects together. We actually had our flagship year this year. The only problem was, of course, we couldn't bring any students to campus. So we all met on Zoom for about 8 hours a day. It was a blast. And this kind of thing really, we think will have measurable impacts. We modeled this on a very successful similar program that went on at Berkeley in the mid-2000s and has been going on ever since. And another one at Arizona State. And they've seen major gains. We're trying to start looking at this because our first cohorts are graduating, so we're going to be able to see retention data soon, and we're very hopeful that we've made some sort of positive impact.
Already, I want to book you for another discussion. Once you have that, we can bring you back and let's analyze the data. Let's find out what's working. Let's find out what's not. But 3 years in now that you have been researching this and working on it, what are the early results you're seeing? What are some indicators of this is working, this is not working? What changes you've had to make? The COVID-19 pandemic withstanding, because obviously that's been a major disruptor to learning across the board. But you are creatively finding a way to work through that, getting people on Zoom calls and having still that connection, that idea that cohorts can be built, that people can learn. So early on, what are we seeing right now that looks promising or perhaps needs to be adjusted along the way?
Mm-hmm. So for a variety of reasons related to FERPA and things like that, the federal education, I don't know, but it's the, we can't share student data without asking students first. So we haven't been able to collect an enormous amount of data about student achievement, but we do survey everyone who's been through any of our programs semi-annually. And so what we've seen is that they do feel a much larger sense of cohort than other students that we've asked in a sort of control population. Now, it's not exactly what we would want because, of course, we've only followed these students for a couple of years, but we're hoping that, you know, as time goes on, we can get sort of a better sense of that. In any case, what our survey data have shown is that students feel this larger sense of belonging, and many, many more have gotten interested in and involved in research as they've gone through our program.
And that sounds like a win, going back to one of the things you had mentioned earlier, is I think that disruption of the status quo of you know, people not wanting to change physics the way physics has been, you know, or how it's always been, in introducing or making sure that there's room for inclusion, and that the voices being brought to the table are not just the archetypal, you know, I think you said geeks, nerds, how we want to think about them when it comes to this. And so building that opportunity, I think, is an important thing. And I certainly want to bring you back for that conversation so we can continue to talk about that. Dr. Charles, as we're nearing about the end of our time here in our discussion, for those that are looking, you know, who perhaps are lifelong learners, they're interested in these topics, whether it's diversity and equity in STEM education, or it's the connection between philosophy and physics, or what you're working on in the quantum Hall effect with physics. Maybe they haven't spent a lot of time and energy like you have studying this, but they want to learn more. And perhaps your talk here has made it more accessible to them, and they're wondering where should they go next? Where do we point them for somebody who hasn't spent their undergraduate, their graduate work and doctoral work studying physics? Where can we point them to get more information on things that might be piqued in their curiosity?
Sure. So I would suggest, actually, before I do any suggestions, I just want to thank you for having me on. Obviously, the whole Jefferson Society. I think this is awesome, and it's so good that you guys are doing this during the pandemic. I want to thank everyone tuning in. Of course, this is an hour out of your day. And obviously, some of this work was supported by the National Science Foundation, so always important to thank the sponsors. Yeah, so thanks to everyone. You can, if you have any specific questions about the talk, email me at my OSU email here, and or of course, Ben can direct you my way. So if you want to get more interested in this, I would suggest, actually, I think one thing that has kept me sort of going is that there are a number of really fun science blogs and resources on the internet that are directed maybe at some lay people. One of my Ohio State colleagues, Brian Skinner, has a very well-trafficked and very interesting and informative blog called Gravity Levity that I want to plug. I also quite like a podcast by Sean Carroll, who's a guy who works in both physics and philosophy, Caltech. His Podscape Mindscape, I'm sorry, is quite interesting, and he has on lots of philosophers to talk about about their work. And then I would actually suggest the philosophy literature on physics. So if you sort of just go looking for philosophy and physics, just type it into Google Scholar or something like that, is often much more accessible than the physics literature and makes a much broader effort at sort of being, available to a larger audience. Just jump in. You might find something interesting.
And so I like that, just jump in, and maybe that's the advice we give to the young learner, the student out there thinking that they want to explore a potential career in physics or something else in the STEM field. But for that person who has the concern for not fitting in, what's your message to them, your encouragement, you having gone through all of your work and now working on making sure diversity and equity are looked at in STEM education? What's your message to that young student?
I would say a couple of things. The first is that your experience is real. I mean, thousands of people across the country suggest that your experience is not unique, it's not you, etc. And so stick with it for that reason. If you have other reasons to get out, if you find something you like more, absolutely go do that. But, don't think that you are sort of unique in this. The second I would say is that it doesn't take a lot to build a cohort, in that you only need a few people who are like-minded to sort of, get along. And I think that can be huge. So if you just sort of go searching out, maybe in non-traditional ways, ask if someone wants to go do a hobby that you like, you might find that there's more room for you than you think that there is. The third is that there are national networks of people who are sort of interested in that kind of thing. So the organization that we belong to, or sorry, that my Polaris organization is part of, is called the Access Network. They have a bunch of sites, I think 12 now around the country. And if you end up at one of them, I know that there are people there who do all kinds of great work. So I think accessnetwork.org is where to go if you're interested in that.
Dr. Noah Charles, thank you. I know you thanked us for doing this, but we couldn't do it if it wasn't for folks like yourself, giving your time, being so gracious with us to talk about the work that you're doing, the fascinating things that you find fascinating, and sharing it with us. We appreciate that. So thank you so much for joining us for this Jefferson Educational Society digital program today.
Of course, thank you so much, Ben.
And of course, thanks to all of you watching along at home. Thank you for tuning in, whether watching live in real time on the JES Facebook page or watching or listening to a later broadcast. We do appreciate that. And of course, we'd encourage you to reach out to Dr. Noah Charles with any other questions you might have. But of course, put them right in the comments section. We'll get them over to him as well. For more information about both upcoming and past discussions available for on-stream demanding, please do visit jeserie.org. There you're going to find a wide range of publications as well, from timely reads on current topics to reports, essays, and more. And be sure to like us on Facebook, follow us on Twitter and Instagram, and subscribe to our YouTube channel. For the Jefferson Educational Society, I'm Ben Speggen. Be safe, be sound, and thanks for listening and learning with us.